belongs to G lambda naught. Now, the being live streamed. Yeah, it was malum hai. Right. Now, this G lambda naught is an open set. This G lambda naught is an open set. So, this G lambda naught, yeah, this G lambda naught, this G lambda naught is an open set. Okay, so there will be, yeah. So my cursor is getting tired. Yeah. So yeah. Now this this G lambda naught is open, so there will be an open sphere centered at X sitting inside G lambda naught. Okay. Yeah. Okay. Okay. Now where is my cursor? Yeah. Right. I think can I have to come for this? Yeah. Okay. Yeah. Now this X is an element in G lambda naught. So what can I say? So there will be an open sphere centered at X, which is sitting inside G lambda naught. So there exists are positive such that SR of X is sitting inside G lambda naught. Okay. G lambda naught is an open set. Therefore, this X becomes an interior point. There will be an open sphere centered at X of suitable positive radius R, such that this SR of X is sitting inside G lambda naught. And this G lambda naught is again a subset of this union. Is sitting inside union G lambda. Lambda belongs to script lambda. Okay. Right. This G lambda naught is one of these G lambdas. So this G lambda naught will be subset of this union. So that's how you are able to produce an open sphere centered at X such that this open sphere is subset of this union. Therefore, this X becomes an interior point of this union. We started with a general point X of this union, and this general point has become an interior point of this union. Therefore, this union is an open set. Okay, therefore, this is in tau. Means tau is closed under arbitrary unions. That's how our tau becomes a topology. That our tau becomes a topology. Our tau becomes a topology on capital X. Okay, so right, what we did. What we did, we took a metric space X comma D. I don't know how to thin this. So many this thing. Lacunae. Okay. Yeah. Here I have different colors. Okay. Okay. So we started with the metric space X comma D. This is a metric space. Okay. And then we collected tau to be. We collected tau to be set of all. We collect. Here is my black color. Okay. This is G contained in capital X, such that G is open. G is open with respect to this metric. Okay. So tau is set of all open sets. G is with respect to the metric G. And then we showed that this is a topology. This is a topology on capital X. This is a topology on capital X. Okay. And this topology is called metric inducer topology. It is also called visual topology on capital X. Okay. So whenever you are inside a metric space, you do have a topology. That is the topology induced by that metric. Okay. And you may ask whether every topological space can be obtained through a suitable metric. Okay. Right. See. Yeah. How about the converse? So we have this situation. Let me draw this figure. So if you collect all metric spaces, right? This is the set of all metric spaces. Okay. So each metric space is a topological space. And each metric space is a topological space. And then, so set of all metric spaces will be sitting inside set of all topological spaces. This is set of topological spaces. How to minimize? I don't know how to make it thin shapes. Okay. Topological space. Okay. Right. Every metric space is a topological space, and there are certain metric spaces. There are certain topological spaces. There are certain topological spaces which are not metric spaces. Okay. Means if you have a topological space, and if that topology is coming out of a metric, that topology is called metrizable. Okay. If you have a topological space, and if that topology is coming out of a metric, and that topology is said to be metrizable. Means the elements of in a topological space X, tau, elements of tau are said to be open sets. Okay, right? So if you have a topological space which comes out of a metric, and that topology is called metrizable. And there are certain topological spaces which are not metrizable, and you can show that they don't come out of a metric. Okay, so the set of topological spaces is larger than the set of metric spaces. That's what you have to understand. So the theory of topological spaces is something more than the theory of metric spaces. That's what you have to understand. Okay, well, as I was mentioning in the beginning, we talked of tau discrete. We talked of tau discrete, the discrete topology, right? In fact, this discrete topology, this is metrizable. This discrete topology is metrizable. All right, you know a metric which comes out of which comes out this topology. Okay, that is in fact called discrete metric. There is a metric called discrete metric. Discrete metric. Anybody knows what is a discrete metric? Hello, friends. Anybody knows what is a discrete metric?
It's the largest one. Apologies.
Yes, please.
Power set is a discrete metric space.
If you have any non-empty set, on any non-empty set, you can always define a metric. If you are given a general non-empty set, without knowing the structure of the set capital X, you can define a metric. You don't need to know what is inside capital X. If you simply know that it is non-empty, you can define a metric on that. That is called discrete metric. It is defined like this. See, what does the first condition say in the definition of topology metric? If X is not equal to Y, D of XY must be positive, isn't it? X equal to y if and only if d of xy is non-zero. So x is not equal to y gives you d of xy is positive. So if I take x, if I take x equal to y, d of xy must be 0. If x equal to y, d of xy must be 0. So I must have this. If x equal to y, d of xy must be 0. And if x is not equal to y, and this condition, d of xy must be positive, you define it to be 1. Okay? If you are given any non-empty set, you define D to be this function. You can see that this is a metric on capital X. You can see that this satisfies the conditions in the definition of a metric. And this particular metric is called discrete metric. In fact, this metric generates certain open sets. You can see that the open sets come out of this metric are same as Course-2 of X. Okay, that you can try as homework. Right. So what I'm saying is, now you go for tau equal to, right? Tau equal to G contained in capital X, such that G is open with respect to this metric D, discrete metric. Okay. Let me use D dash or otherwise D dash. We call this D dash. Okay. For discrete metric, let me use D dash with respect to D dash. Okay. So you collect all open sets, all those subsets of X which are open with respect to this metric D dash. Okay. And you can see that this is Course-2 of X. You can see that this is Course-2 of X. Okay. Means that this is discrete topology. Nothing but is discrete topology. Course-2 of X is discrete topology. So this is discrete metric. The usual topology coming out of this metric is the discrete topology that you can verify. Okay. Yeah, means you have to take a general subset of X and you have to show that it is open with respect to this metric. Okay, that you can try as homework. Right. Next, I want there are some how many more minutes? Some 11 more minutes, right? I have to stop at 1:30. Okay, yeah. You have a very important example, maybe for number 4 or 5, 4. Yeah. Before that, yeah. You so what did we do till now? We have seen that every metric space generates a topology. Okay. And yeah, before going to the next example, let me point out that on Rn, you have the Euclidean distance metric. Okay, and this metric generates a topology that is called usual topology on Rn. Okay, this is the Euclidean distance metric. Okay. On Rn, you have the Euclidean distance metric. This metric generates a topology, and that topology is called usual topology on Rn. Okay. It is the usual topology. It is the right on R in your undergraduate program. You have studied analysis of the rail line. Of course, under the modulus metric. Okay. So, in fact, you have studied the topology, the various topological aspects of R in your UG program. That is under the modulus metric. Okay, you can study the same concept for R2, R3, and so on. Okay, on Rn, on the n-dimensional Euclidean space, you have Euclidean distance metric, and this metric generates a topology, and that topology is called usual topology on Rn. Okay, and yeah, to give examples of right on R, right on that is on the number line. Every open interval becomes an open set. Okay, and in R2, every open rectangle becomes an open set. Okay, open rectangle means You take points inside a rectangle. I am calling these as points inside a rectangle. I don't want, I am calling these points points inside a rectangle, and I am not taking points on the perimeter, right? And the points I said I say that these points form an open rectangle. Okay, and that open rectangle can be shown to be an open set, right? Similarly, you can talk of open square and so on. An open disk, right? You take the points inside a circle. You take the points inside a circle. Okay, you take the points inside a circle, and these will be forming an open set, and this is called an open discontinuous dot. Okay, if this point is some x, it is SR of x naught. SR of x naught, where R is okay. This is called an open discontinuous x naught of radius R. It can be shown to be an open set. Okay, in R3, you have open sphere. In R3, you have, right, the Euclid distance is the usual distance. The Euclid metric is the usual distance. And here, if you go for SR of x naught, in R3, if x naught, the point in R3, and your R is a positive number, so this is an open sphere. These become in the hello. In this sphere centered at naught of radius R. Okay, so you have this situation. So this is x naught, and you are considering an open sphere centered at x naught of radius R. So you consider this open sphere. You consider sphere centered at x naught of radius R. Okay, and a point. You collect all points whose distance from x naught is less than R. This is why d of I comma x naught is less than R. You collect all such points. Okay, all these points, Okay, this will be forming this open sphere. This will be forming this open sphere. It is the usual open sphere. You are not taking the points on the ball, on the surface of the ball, but you are taking the points which are in the interior of the ball. Okay, or ball means it is sphere, right? In the spherical sense. Okay, so this kind of set of points is said to be is an example of an open set. Okay, and open cuboids, open cubes, all become open sets. Okay, these are a few examples of open sets, right? And then you can come to an important topology called cofinite topology. Cofinite topology. Is there anybody who knows to cofinite topology? Hello? Let X be an infinite set. Let X be an infinite set. Okay. Let tau be consisting of phi union G such that X minus G is finite. Okay. So let tau be consisting of the empty set and those sets G, which are subsets of capital X, whose complements are finite. Okay, and you can see that this kind of a tau is a topology. This kind of a tau is a topology. Is a topology on X. Okay, and this topology is called cofinite topology. cofinite topology. Okay, I'm taking the empty set and those subsets G of X whose complements are finite. Okay, and you can see that this tau satisfies the definition of a topology. Therefore, right, and this topology is called cofinite topology. And in fact, members of topological space tau are called open sets. And so if you have a topological space x comma tau, if you have a topological space x comma tau, okay, and then if G belongs to tau, right, G is called an open set, right? If you have a topological space x comma tau, members of tau are called open sets. Okay, this is definition. Members of tau are called open sets, and right, and a set is defined to be closed if its complement is open, right? F contained in X is closed. Is closed if and only if its complement is open. Okay, if you are inside a topological space, members of tau are called open sets, and a subset of f of x, a subset f of x is said to be closed if its complement is open. Okay, so closed sets are complements of open sets. So that is definition. So that's how here in this topology, cofinite topology, you want G to be tau to have those sets G whose complements are finite. Means right, this G is open. We can see that this is a topology, therefore G becomes open, and these are complements of G, so these are closed sets. So finite sets are closed sets. In this topology, finite sets are closed sets. Okay, this is a topology where finite sets are closed sets. Right. Similarly, here you can replace cofiniteness by you can replace infiniteness by uncountability. You replace infiniteness by uncountability, and here you replace by finiteness by countability. Then you get co-countable topology. So you have this situation. This co-countable topology. Example. Let co-countable topology. Co-countable topology. Right? Your X must be an uncountable set. You replace infiniteness in the previous example by uncountability. Uncountable. Okay. Let your capital X be uncountable, and then tau C. You define tau C to be set consisting of phi union those sets G contained in capital X such that its complement X minus G is countable. Okay. Right. So you take any uncountable set capital X and let your tau C consist of the empty set and those sets whose complements are countable. Okay, and you can see that this is a topology, and this topology is called co-countable topology. Here, right? Once you know that this is a topology, so this G becomes an open set, and it's here its complement is countable. So countable set. So this is a closed set. This being complement of an open set. This being complement of open set is closed set. X minus G is closed. So countable sets are closed sets. Okay. In this topology, countable sets are closed sets. Okay. In fact, these two examples give rise to topologies which are not memorizable. Okay. Right. Here I would like to stop. Okay. There are some problems which I could not control. Okay. Hope my lecture has helped you. Right. Right. Yeah. Anything else you want to tell me? I would like to stop here.
No, sir.
Hope I am understandable. There are some problems regarding my pen and use of pen, colors and so on. But for the content, I did not do any mistake. Hello. Can I stop here?
Yes.
So please go through the material in your book 2, in your textbook on unit 2. Okay.
Okay, sir.
In the next lecture, I will try to cover some part which which are important for exam. Okay, right?
Okay, sir.
Let's stop here.
Okay, sir. Thank you, sir.
Thank you. Bye bye.
Okay, sir.
Okay, thank you, sir.
Bye.
Bye.